Okay, guys, welcome back. We now have an exciting session by Anna, and it's entitled Sign Here.
Hi, everybody. So this session is going to be loud from what I hear. I can hear myself pretty loud here. So if you intended to sleep, like I said, this might not be the best choice. I would like to thank you for coming here since it's the second day and lunch is next. So I think you're eager to go and kind of get better from last night. If you partied hard, I'd heard that some people were up until 3 a.m. I don't know if they're here or somewhere on a sofa on the floor above or below. So my session today will be about certificates, key stores, and digital signatures. I know, really hot topic, very interesting. I come from a small country in the south of Europe called Croatia. It's a lovely place to visit during the summertime. We have a great coast, warm sea. I know that you have a great coast here. It's actually my third time in Oslo, and the city is as beautiful as it was like 20 years ago, which speaks more about my age than the city. So I work at a company called Aseco. It's a quite large company. We operate mostly in the southeastern European region. We do security, post terminals, solutions basically for banks and big companies that need, the whole package. I'm currently serving as a project manager and business analyst in my company, and I had been doing Android for about 6 years now. So, today, as I said, we'll be focusing on key stores and certificates. So, let's just start by defining a certificate of what it is. It's basically some kind of electronic document, and it proves ownership of a public key. Now, that's a wonderful definition. Now it's all clear. We know what it is, we know how to use it. Not really. It speaks nothing, at least not to me. So, it has a certain structure to it. It has use in TLS, basically transport layer security. And each time any kind of browser communicates with a backend server, there is some kind of communication performed where there are things checked, mostly certificates, and basically we want to know who we are communicating with, and that's where those certificates come into play. It's also used in electronic signatures. So some countries in Europe are using digital basically digital signatures as valid, handheld signatures. They can open a bank account, they can open a phone bill just by using some kind of certificate, not being required to go to a bank or a company. So this is actually replacing your fingerprint, your handwritten signing. It's becoming more and more useful today. And as I said, the certificate has a specific structure. You can look at it on any kind of website that you use. It mostly holds kind of version number, identity of the host or the company that issued it, its validity, not before, not after, and basically other, let's say, cipher information that's being used in that particular communication. Now, so any kind of certificate begins with an identity. It can either be your identity as a user, your company, any kind of host, uh, let's say name, address, phone number, your blood type, whichever information you want to provide, you can provide in there. There are some mandatory information that you must put in. And as I said, you need a public key. Now, that public key comes from a pair of keys. One is public, one is private. Now, we won't go too deep into cryptography, but let's just name a few things so we are all using the same terms. In asymmetric cryptography or public key cryptography, you're basically using pairs of keys to do some kind of operation during communication between a server, Android device, any kind of channel that needs to be secure. PKI or public key infrastructure is basically a set of rules, roles, basically how you manage and distribute and use keys of this sort. The keys are asymmetric, meaning that the public and the private key are not the same. And that brings a layer of security that doesn't in the instance where the keys are the same. So, uh, how do we get those keys? Well, we need to calculate them. So that calculation must be economical, meaning that the computational power that you're using, the computers, the time, it's all valid resources, and you must be, prudent in using them, meaning that you need to be able to calculate this in, let's say, few seconds or minutes or whatever, depending on the use, and not take, let's say, 1 week. If you're taking a week to calculate something because it needs to be really complex, then you cannot really use it. So we're balancing here. Now, once we have those keys, they need to be used in a certain way. In this case, the private key always stays with the owner and exclusively with the owner. If the public key gets kind of misused and left out in the open and somebody gets it, then you're in a lot of trouble. The public key obviously can be shared, which is kind of self-explanatory by the name. The private key is used to decrypt messages. So when you get a message from a remote server, you will be using your private key to decrypt what was sent, to see what was actually sent. While the public key will be used to encrypt that message, meaning that any one of us can use a public key, use a message and encrypt it and send it to a server, and only the user or the company or the entity that has the private key will be able to decrypt and read it. That's the intention. And the other thing that we're using the keys for is signatures, meaning that the private key, so the one that only one person or one company has, is used to calculate the signature of any kind of message. And when that message is received on the endpoint or backend server or whatever, the public key is used to confirm that signature is valid. Now, we're down to digital signatures now. They are basically a mathematical scheme that demonstrate authenticity of any kind of message or document. So the signature is what you put on a document to say all the information and it is correct, and yes, I want to sign over my paycheck for the rest of my life and the bank will take care of it. Now, those signatures have a very important purpose. First of them is authentication. Now, in terms of authentication, we want to know who the user or the entity is. We need to know who they are. Because if we know who they are, then we know whether or not we can communicate with them. The second one is non-repudiation, meaning that we are certain that the person who sent the message is who they say they are. If they are not who they say they are, that means that somebody stole the key and used the private key to sign a message and send it to somebody else. So if the key is secure, we know that the user sent it, he cannot deny it, or she cannot deny it. But if there's something wrong with it, we know that the key has been kind of broken or stolen and we cannot trust it anymore. And the final part is integrity, meaning that when you get the information, you know that nobody altered it during the transportation that occurred. Now, if you want to create a digital signature, you basically calculate some kind of hash or digest using any kind of algorithm that's currently stated as complex enough. You encrypt it with the private key, fair enough, and the recipient uses their public key to decrypt it. So the keys can be used both ways. It only matters where the private key is and where the public key is. Both can serve each purpose. Okay, now let's go back to where we started, back from the rabbit hole. We said that any kind of certificate consists of identity and the public key from a pair. That public key belongs to that entity. But how do we actually know that it belongs to them? What's the proof? Do you believe me when I say that a certain public key belongs to some entity, or do we need something more, authoritarian? Well, there is something called a certificate authority or an entity that basically says, I will confirm that this identity and this public key truly belong to one another. And those certificate authorities are entities that we trust. Their sole purpose is to basically issue digital certificates, and they, as an authority, are trusted. Now, Can any of you become a certificate authority? Well, technically, yes, but it requires membership in a very rigorous program where you need to meet certain detailed criteria. And although it's possible, it's a hassle, so it's usually it's easier to use a certificate authority and get issued a certificate for your website from somebody that has already jumped through all the hoops. Now, the certificate authority will first do its basic function, and that is to create a certificate for themselves. Now, we have this entity who we need to trust, and the first thing that they do is create a certificate for themselves and say, okay, trust me and trust my certificate. That's the process. It might seem kind of loopy or self-serving, but that's the way it works at this moment. Now, after they sign their root certificate, the original certificate, they kind of get distributed to our browsers and to our OS and to the Android phone and to the iOS phone. So basically, when you go to any kind of website, or basically you look at Mozilla or Firefox or Chrome or your Android or iOS device, you can get a list of all the root certificates and trusted authorities that are currently present on your phone. So that list of who we trust is already pre-shipped with what we're using. It also means that the next time when somebody gets kicked off that list, there will be a security update, and we, as early adopters, as we all are, will probably update immediately, meaning that if something broke in the meantime, we will be safe because that kind of root authority will be removed from the list. So that's really important to do. Now, if you want to get the certificate, you will probably go to either Komodo or one of these entities from the list. Somebody is getting distrusted at this very moment. I cannot really recall who that is, but somebody has been bad. And if you don't want to cash out for a certificate, you do not need to do that. You can go with Let's Encrypt. They're free. I have had mixed reviews in terms of how easy it is to get the certificate from them and set it up. But I guess that there's always some kind of drama with certificates. So just one question, who here has ever set up a certificate on a website? Okay, so out of you three, has anybody ever had problems with it? Okay, 33%. Wow. I know that it's not. It's statistically, it's a big percentage, but since only 3 people here were raising their hands, I guess that we should, as the web developer part of the community, I know that they have horror stories from this, and let's just skip it for now. So, how does a certificate actually look like? So, if you open facebook.com or google.com and click on the little locket or name in the bar, you will be able to get certificate information for that website. Now, this is a screenshot of google.com, and it's not really, I don't know if it's visible in the top rows, but you can use google.com on your phone and check for yourselves. So basically, you see that the lowest certificate, the first one that you see, is signed by, let's see who it was signed by, Google Internet Authority G2. Now, Google is obviously going into the game of becoming a certificate authority. So the Leaf certificate is signed by Google. Now, if you go one level up, and basically that's in the top bar, click on the Google Internet Authority G2, because we want to know what that is, you see that, again, it's an intermediate certificate authority, and that it was issued, here in the issuer name, by GeoTrust. And that's a certificate authority. So if you hop one level up, you can look at the root certificate, and you can see that it's a root certificate because it obviously says so. Basically, that's the root one that was first issued, and it's trusted, and we use it. Now, if you take a look at it, from a different perspective, you see that we actually have chains of certificates, where the top one is kind of the Leaf certificate. Its digital signature was verified by an intermediate authority, and the intermediate authority's signature was verified by the root. So we have a chain of trust that works exclusively if each item is trusted along the way. Now, not all certificates are created equal, of course. When you look at websites, you can see the difference. Some websites have just the green locket, and some have their name listed up there. In terms of certificates, there's not much difference, but the process required to get an extended validation certificate, and that's the one that holds the name, it's more extensive. So you need to provide more information and jump through more hoops to get that kind of certificate. And that that kind of basically the whole flow is not really bulletproof, and it's not human proof. Basically anything with humans is prone to errors, so is this whole system. So basically those membership programs that I spoke about, they kind of they tend to probe you and see if it's still, if things are okay, if you have access to what you should have access to. And they are known to send emails with information to, let's say, specific email addresses that only a domain owner should have access to, like root at facebook.com, admin at facebook.com, and any other combination that sounds, very important. And that's not always the case. We are going to talk about that a little bit later. So basically, sometimes the owners of a domain get kind of carried away, or they're not careful enough, and users like you and me, we can request an email address that might not be, good to have from terms of security. No. Are we safe if we have TLS, if we have certificates, if everything is set up correctly? No, we are not safe. And I believe that this tweet speaks volumes in terms of what we are achieving with certificates. It's not that we are safe, it's that we have privacy. But in terms of identity, we have any, tangible proof that who we're speaking to is actually who they say they are. So I really, really love this one. It's an old one, really old one, but it captures the whole sentiment. So the problem with the whole scheme is subversion, meaning that things can be overthrown. Now, if somebody steals a key, that means that they can use it to sign stuff with that key. Now, there were a few boo-boos in the history. Mostly in 2001, VeriSign had an issue. I believe it provided two certificates to a Microsoft email that was supposed to be basically belonging to Microsoft, but it was a user that managed to open an email account, and they got sensitive data that they shouldn't have. So Komodo and DigiNotar had a problem in 2011. We won't go into details. And Trustwave in 2012, there was some mix-up with man-in-the-middle attacks and issuing certificates that were used for transparent traffic management. So things tend to go bad if people are not careful. So the scheme is definitely flawed. Any kind of mistake in any of the steps can provide issues. And how do we prevent that from happening, basically? So your keys need to be safe, and by safe, I do not mean keeping it on a USB stick and putting it to Git or putting it to a Dropbox folder and say, "Hey team, all 20 of you, here's the location of our key or Keystore or whatever." Basically, it needs to be kept in a really secure location. So big companies, banks, they don't mess around with this, and they're not so frivolous about it. They use something that's called a hardware security module. It's basically a box from hell that when you look at it wrong, it will reset everything on it. So we're talking about the spy movies when you have four people entering keys on four different locations at the same millisecond, and the temperature needs to be right, and the box must not be tempered or moved or looked at, or I don't know, moon must be aligned with Venus or whatever. Basically, any kind of misalignment without prior authorization, everything on that box will be reset. Now, if it's your pet project, you will generate a new key, generate a new key store, you will publish your app with a different signature. But if you're a big company, you cannot really allow a situation where everything you're working to, your whole ecosystem kind of breaks in a second. So it needs to be really, really taken care of in a secure manner. And most importantly, those things are kept offline. They're kept offline because if it's online, if it's accessible, somebody can get to it. Maybe not now, but eventually somebody will be able to get to it. Now, Android takes care of us. In terms of when you have an self-signed certificate or unknown certificate authority, for instance, you don't want to go with Let's Encrypt and you don't want to pay, you create your own certificate, place it on your website and say, I have an API and my Android device will connect to it. Android will say, no, I won't, because you are not the certificate authority your device trusts. Now, some time ago, before Android M or N, you could have installed a certificate on your Android device and things would work. And you obviously can pin a certificate to your application. But from Android N, basically you need to use your network security config, so the XML, and list whether or not you want user certificates to be trusted. And if you're pinning your certificates, then you need to list all of them inside for them to be trusted. So Android will also say no if there is something wrong with the chain. So we already said that there is a chain of certificates everywhere. Browsers tend to cache stuff, so if there's an intermediate certificate missing somewhere, no big deal. Maybe they will prefetch it, maybe they will have it from some other time, they will use metadata to get it. But Android is being proper here, so they want the whole chain and they want it in the correct order. Now, certificates are obviously very important. Who here has ever pinned a pin or a certificate in their Android app? A few of you. Okay, great. So you had fun with that, I'm sure. So, signing Android applications. All of you, I presume, have produced an Android app before. Anybody hasn't? By produced, I mean created an APK and deployed it at least to a device. Okay, let's say most of you are. So what you have been using is the debug keystore provided to you by Android in the SDK. What password does that keystore require? Android, the super secure password which nobody will ever guess. Each one of those certificates that you're using is different because it belongs to your identity and your machine. So basically you cannot interchange them. And if two of you try to produce an application from the same code base, you will have to either deinstall it and install it new because the signatures won't match, because the certificates don't match regardless of the password. Now, before we can deploy anything on Google Play, our application needs to be digitally signed by a keystore. And it cannot be the debug keystore, it needs to be, a proper keystore. So what do? We simply generate a new key and keystore, and we sign our application. Now, if you came to a project and the application and project were already set up, you had everything that you need also set up. But if you need to go from the beginning, you first create a new keystore, and in that keystore you need to define the certificate data, so that's your identity. You need to define the password for the keystore and for the key, and you need to set the validity for years. So those who were kind of playing with fire and said, oh, my application will run for 10 years, we're kind of getting to the point where we need a longer period here. And with Android P, we have a solution for that too, but a little bit later about that. So basically, you create a new keystore, or if it's already created, you just sign your application by choosing which key and keystore you want to use in this particular case. Now, if UI approach is too hipster for you, you can always go back to the tools in the terminal. You can use key tool to generate a key. If you ever connected to the Google Play services and needed to provide for maps or something your key, you have already used this. You have the zip align that uses black magic to align all uncompressed data, and it's performance related. We won't go into that. And the APK signer or jar signer, which will basically sign your APK. Now, we have some really important decisions to make. First of which is who will be responsible for our signing key. So, show of hands, who here has access to the signing key for their Android application that goes to Google Play? Okay, out of you who have raised their hands, who works in a team where an additional member has access to it? Yay! Somebody's going to have fun later on. Okay, so what was the process for years before now? Well, the developers had total autonomy of what will happen with the signing key, meaning that you had access to it, you used it when you needed to, and everything was fine. So our expectation is that we need to be able to sign our application throughout its lifetime, whether it's 5 years, 10 years, until the company goes bankrupt or whatever happens. Well, prerequisites for that is that the key is safe, seems logical, and that it is accessible. Now, these two requirements are kind of clashing because if the key is accessible, that means that somebody can get to it. And by definition, it cannot be completely safe. So we're kind of balancing here between being able to update our application and being super secure. So secure that nobody ever will be able to update our application, not even us. So in reality, people spill coffee and people leave companies. Now, when I say reality, it's not reality, it can be a nightmare. Now, it's confession time. So, a long time ago, in a company far away, a person named John worked on an application. Came the time for the application to go to Google Play. John completed his work, he uploaded the application, and the client was happy. Now, sometime after that, John spilled coffee on his MacBook because he was clumsy, and some time after that, he left the company. Now, the coffee spillage and the leaving of company aren't really related, so he didn't get fired for that, but let's just say the computer got stored somewhere in storage and John moved on. Now, a few months after that, came the client and said, "Oh, I want you to develop this cool feature for me." And of course, we were happy to do that. We developed, we finished. Came time to push it on Google Play, and we had a problem. And the problem was that we could not sign our application because the Keystore used to do it the previous time was nowhere. So we went through the project. Maybe it was somewhere in there. It wasn't there. We went through Git, managed to find at which timestamp there was a reference to a Keystore, but the Keystore was not there. So it's not like somebody went there and rewritten past because they wanted to. We simply didn't know where the Keystore was. So we went back to Bill Gradle because why not put everything in your Git repository and your Keystore data in Bill Gradle? And we actually saw that the Keystore was completely not where it was supposed to be. So what do? You don't know how to get it. The person who built who made the Keystore is no longer there. I'm going to tell you that this story has a happy ending, a really weird happy ending where we managed to get to John, and John gave us his password, and we brought the computer to the nearby Apple store, and we kind of plucked it out eventually. So we had luck. But this kind of problems happen to bigger companies, more serious companies, companies with a very affiliation name. So not your pet project. It happens because we're humans and we make mistakes. And that's okay as long as you learn something from it. But it obviously happened enough times for Google to say, "Hey, we got you back. This obviously is an issue, so let us help you." So they introduced something that's called Google Play App Signing, where they say, "Okay, we will take care of your app signing, we will hold your signing key, and you just take care of the upload." So it works well. You have a simple procedure when you're adding new applications. You opt in, you create an upload key. So that's something you will sign your application. and you push it to Google Play, upload the APK, and an app signing key is registered. And Google manages that, meaning that they hold it somewhere safe, probably in that hardware security module that we talked about. At least we hope. And for existing apps, you can always hand over control of your signing key. You submit that signing key that you already have. You create an upload key, and you continue signing your application with that upload key. What you need to know, if you choose to go either way, the decision is permanent. So you cannot say, oh, Google, I changed my mind. I'm feeling lucky. I like roulette. Please give me the signing key and I'll continue doing it myself. No, you cannot go back once you choose. But what happens if your upload key gets stolen or compromised? Well, this is the beauty of the process. Google says, no problem, inform us of this, and we will revoke that key and generate a new one. So if it gets stolen, if it gets lost, if it gets compromised, you have clear steps in destroying that one key and getting a new one. And even if your key gets compromised and stolen, you have to think about the fact that hopefully your attacker doesn't know your Google Play credentials. But if they know your Google Play credentials, I would assume you have bigger issues than just one signing and upload key. So one decision has been made. We either feel lucky and brave and continue to take care of the process ourselves, or we let Google handle it. And now there's a semi-heated discussion whether or not you should use the same key to sign all your flavors. So if you're working on a big project, you will have your development environment, your staging, user acceptance, production, and of course you will be testing on everything except production. We don't do that, that is bad. But what do you use? Do you use the same key? Do you use multiple keys? Well, decision is on you because you know your process better than anybody, and that's basically it. If you want, to have your pros and cons, if you use the same key for everything, basically you have your modularity. You can share permissions between your applications if that's something that's really necessary, and you can update it without any problems. But again, we are going back to that single point of failure. So if one thing goes bad, everything went bad. So at the end, it's on you to choose whether or not you want it or not. So we've covered keystores, we covered signatures, certificates and signatures. Now we need to take a look at the Keystore system in Android. So the Android Keystore system keeps our cryptographic keys safe from extraction, meaning that if you need to create a cryptographic key or something else, it will make sure that any kind of attacker or malicious person cannot extract it from your device or application. Why would we need that to begin with? So are we holding any kind of sensitive, important data in our app? I believe that's the question we should start at. So do we have something really sensitive, a small piece of information that's really, really, really important? Well, a UML diagram usually helps us decide really fast. So if we don't need that piece of information, do not keep it in the app. Why would you ever keep it in the app if it's not important? If it is important, let's not keep it in the app where it can get stolen. So basically, if you can refrain from keeping anything sensitive in your app, please do so. So extraction prevention is something that's crucial with this thing. Now, the system is generally in charge of any kind of cryptographic operation, meaning that, let's say, the key material that we're using and that we have is bound to either a secure element or the trusted execution environment. So we're not holding it in the upper layer, we're letting the system or the hardware take care of stuff. The system process is responsible here. We're not kind of dabbling into that. What we get from this is more security, obviously, and we can choose how long any kind of operation or retrieval of data will last. So we can say after the user unlocks the, let's say, lock screen, he has 15 minutes or 15 seconds to do something with a key or something else. If you want to be really safe and know that the data is stored in the hardware part, we have the utility methods from the key info class from API 23, which basically say is inside secure hardware. So we know that a key is somewhere where we know it's safe. And the longest method ever provided, you can read it yourself. I know it's not prudent to put much text in presentation because people then read, but I'm going to let you go through this. We have time. So basically, you can check whether or not something that you have is where it's most likely to remain safe. Now, there is an option of choosing between a keychain and the Keystore provider. And again, Keychain is available from API 14, so it obviously encompasses a bigger batch of devices out there. And if you want to know what the differences are, basically the keychain will use system-wide credentials, meaning that one set can be used for multiple purposes. And it has the system-provided UI, which we know that is beautiful and elegant and the way it should be. And of course, if you want to go the other way, from API 18, you can use the Android Keystore, where you can define app-specific credentials, which is obviously better. So who here uses the same password for more than 2 sites or social media, something? Bad, very bad. Change your passwords after this, but not on the public Wi-Fi. Go home to your network. Okay. So app-specific credentials, where you can define something for a particular purpose, is always better, because if something gets broken, only that thing will become broken. There's no interaction, meaning it's under the hood. You don't have to interact with the user. And obviously it's available from API 18, meaning less of those 2 billion devices are available to you. Now, what do we typically need with these operations and cryptographic data? Well, we want to either generate a key pair for any purpose. We need to list existing entries because we need to check something. We need to sign data, and we need to verify signatures. So basically all those things that we did with the keys before, we're now doing it in Android. Now, the API used for this, I won't say simple because people don't like the word simple. It kind of says that it's no effort. It's straightforward. It doesn't require much, elaboration. It's clean. So if we need to generate a key pair of any kind, we need to create an instance of the key pair generator and choose an algorithm that we like. By like, I mean the one that's recommended as, complex enough and safe enough. Basically, guidelines tell you what to use. Now, once you have done that, you initialize that generator by providing an alias and providing a purpose. Now, we're back to that thing. Do not use the same thing for multiple things. Here you can define whether or not you will sign stuff and verify stuff or something else, but keep it simple. Use one key for one thing and the other for something else. So keep it separate if possible. You set a digest, whether it will be SHA-256 or something else, and you build the thing. Once you build it, your key pair is generated. So straightforward, not much magic there, at least not visible. It's under the hood. If we need to list entries, we retrieve an instance of the Keystore and load it. Once it's loaded, we just get a list of aliases. So again, not much magic there. Now, if we need to sign data, we create a signature and initialize it with the private key from the entry that we already have. After that, we update the data, whatever the data is, whether it's a message or something else, and we get the byte array signature for that data, which we can then either check in the app, which is not as good as putting it somewhere, let's say, to an API to a backend server that will check that signature against something else, because you can say I'm safe, but it's better if somebody else checks whether you're safe or not. And verification of signatures. Again, you retrieve the signature instance and you provide the certificate from that entry that you have. Once you've done that, you basically just verify whether a signature is valid or not. So pretty straightforward. Kotlin, Java, whichever you prefer, both is viable and you can use either. Uh, what you need to know is that sometimes a little more confidence is useful in using all this. And key attestation is something that can help us a lot. Basically, it checks whether or not any kind of key is stored in a hardware-backed key store. Now, it gives you more confidence, but the problem is only a small number of devices running API 24 onward has this. So again, you're kind of choosing what the balance is between, absolute security, whatever that means, and the maximum reach of users that you can encompass with that. Now, Android Pie, I must confess that I was really heartbroken when I found out it wasn't going to be Pancake, so that's my personal trauma here. Basically, it brought us some cool stuff. It brought us key rotation, meaning that you can do some weird magic things with the keys if the team is using the same thing. Basically, you can rotate the keys. We won't go into details here. And it brought something called the Strongbox Keymaster. So, woo, big words. Again, it's a hardware security module. Basically, you have a hardware-backed standard that will keep things safe in a separate process in the hardware. The problem is it's not standard, it's not mandatory, meaning only a few devices will have it. So the power that it brings is basically inaccessible at this point. So many more things for you to explore. And basically anything related to security is a balance between what you can do and how complex it is and how many users will benefit from it, because Android is still pretty much fragmented, meaning that you need to find that business requirement that will say, okay, I will sacrifice half of my users in favor of this, or you will have additional implementations of something on a lower API levels and something on higher, or maybe you will say when the user on Android 4.1 tries to log in, oh, sorry, buy another phone or update your phone or something else. Basically, depending on what your application does and what your requirements are, you need to see what you will use. And nobody can choose that for you, of course. But what you can do, and I strongly urge anybody with any kind of external API communication with a backend server, go to Qualys SSL Labs. It's the best site ever for checking the security of your web. It will give you the grade of your web, whether it's A plus, A, or downward. It will tell you, in addition to full analysis of the ciphers and the rest of the items that you use, it will tell you what Android devices and what browsers can connect to your website. So if there's something messed up on the website, it will tell you so. It will say if some Android version that should connect cannot connect because of a mistake. So it's a great tool and it takes like 20 seconds of your life, and it alleviates that drama and embarrassment when you push a product out and your client calls you, why can't people log into my app? This is kind of not what I was expecting. So check, improve things, and of course decide what works best for you. And at this point, I would like to thank you for your attention and for not falling asleep. So I believe lunch will be served in 15 minutes. And if you need anything, you can find me either in the halls or here in the next 5 or 10 minutes. Thank you.